Okay. What is the definition of a polar covalent bond? Ooh, now this is a doozy of a question because there are many ways to define it. Okay. For example, let's give a visual example. Okay. NH3. Okay. Actually, that's not even the right thing. I wouldn't even mention that actually, because that's almost unrelated. There are ways to make non-polar bonds but still have a polar molecule, if that makes sense. But thinking about it, there's also ways to make polar bonds and have a non-polar molecule, because polarity usually indicates direction. So let's actually write the question down first. Definition of a polar covalent bond. Okay, so now the way this works, okay, this is gonna be might be a little rusty just because it's been a while since I did this, but there's different ways to break down what type of bond you have, and you find that out based on electronegativity. So electronegativity difference is how you find out if polar or non-polar. Okay, and you're probably wondering, what is electronegativity? You should have a sheet as well, because some periodic tables don't include it. But if we hover over these elements, for example, right, hydrogen, let's start there. You see this has an electronegativity of 2.20. I don't know what that's doing. Oh, that actually shows the electronegativity. Okay, there we go. So let's actually switch over to electronegativity. That's actually perfect, because it's actually on a, exactly, it has, right now it's showing logarithmic. This is more linear. The point being is that if you had your periodic table, so mind my drawing here, let me just scroll down more because I'm on question 14. Actually, you know what, I don't want to show the borders. So if we had the periodic table, okay, that's kind of the periodic table. That's a pretty good picture. The electronegativity increases in this fashion of a, I guess, trend. This is how it trends. The lowest electronegativity thing is right here. Okay, this is the element here, and this is francium. And the highest electronegativity is actually going to be chlorine, I believe. Or fluorine. Yes, fluorine's at the top. So here is like around here, and that's fluorine. Okay, we don't really count the noble gases really. These ones can be ignored, and we also don't really factor in. I mean, kind of we do factor in hydrogen, but typically we don't really factor in the noble gases, which is why fluorine is the highest one and not like neon. So let me actually just redraw that. So fluorine is like up, oops, this is fluorine in this corner. Okay, the topmost thing, and francium is the bottommost thing on that end. Point being is that this is the electronegativity I guess relationship. It increases that way. Just remember that, okay? If you ever think of electronegativity, just think of a big arrow going that way, okay? So with that being said, this is the directionality of electronegativity. Now, how does that actually let us know about a polar covalent bond? There's ratios, okay? If the difference between them is between 0 to 0.3, okay, this is considered a non-polar covalent bond. Okay, if it's now between if it's between 0.3 and 1.6, this is a polar covalent bond. And if it's typically it's above 2.0 and greater, so greater than 2.0, that's an ionic bond. Okay, and now you're probably wondering, okay, so what happens between 1.6 and 2? So it's not a rule set in stone. Okay, even for the 2, pretty much is that if you have metal and non-metal, it's ionic. As we discussed, ionic bond is metal and non-metal bonded together. But there are some strange situations where you have a value that's still greater than 2.0, but it's still going to be a polar covalent bond because it's still 2 non-metals. So just make sure you're always checking whether the actual elements together are, metal or non-metal. Now, with all that being said, okay, let's look at, for example, if we want a polar bond, right? Let's say we had CCl4. Because remember how I mentioned briefly, that you can have polar bonds but a non-polar element, okay? Because there's different things, right? CCl4, every chlorine to carbon, right? You have that 3.16 minus 2.55. It's not the biggest difference, but it's enough, right? 0.61. Technically, that is a polar covalent bond. There's polarity. The chlorine tends to be more negative and the carbon tends to be more positive. But if we were to draw this out, actually, we'd have a perfect, a perfect tetracarbon, a tetra structure, okay? And this, because actually there is equal pull in every direction, okay? And remember that this is a 3D structure. So in this 3D plane, is like there's an equal pull in every direction. This is a non-polar I'm really blanking out. Non-polar molecule. Okay? I'm just going ahead to try to explain, because just because you have polar bonds does not mean you have a polar molecule, and vice versa. I'm actually going to show you now an example of something that has non-polar bonds but still a polar molecule. So let's think of nitrogen. Is nitrogen a good example? No. Let's see. If we did, that's really just on the borderline there. Let's try it though. Let's see if we had, it's right there in the but NO2. Okay, nitrogen dioxide. Is that actually a bond? No. There has to be an easier one we can use. Is it boron 2.4? Yep, there we go. No, but that's also non-polar. Interesting. We'll definitely figure one out, because I'm thinking like if we get nitrogen dioxide, yeah, actually that could work. But then it's not an equal distribution of bonds, so guess we'll never know. The point being is that if we had NH3, right? The reason why I didn't want to use H is because H is all the way at 2.20. So these are already polar bonds. The key here is that it has a lone pair, which makes this like skyrocket up, as in like towards the lone pair. So this is a polar molecule. Okay, and as you see here, it definitely also has polar bonds, because I couldn't think of an example where it would be nonpolar, but exactly so. The thing is that nitrogen is 3.04 minus 2.20, which is like 0.84. So exactly, it still falls in the range of a polar covalent bond. Okay, so it has polar covalent bonds and it's also polar because of that lone pair. Maybe next time I'll come up with actual something that, you know, would count as, oh, maybe sulfur. Nope, fluoride is too strong. So with that being said, overall, to define a polar covalent bond, and the key word is bond, this is the limit right here. Oops, don't know how that happened. Let's just do this real quick. There we go. So 0.3 to 1.6, that is what you would define a polar covalent bond, and that is from your electronegativity. Okay, so I know they mentioned just like water, for example, but you see, they're actually trying to say that is right though, as in it is a polar molecule, but that does not determine whether it's a polar covalent bond. What you need to do there is find the electronegativity of oxygen, which is 3.44 minus 2.20. Okay, 1.24. Because there's a difference of 1.24, that falls in our range here of 0.3 to 1.6. Okay, which is why we can say that yes, water has polar covalent bonds. It's not just from this, it's from the electronegativity. So I'm going to say this is incorrect, because you need to use electronegativity to determine polar bond or not. Polar covalent. Because I can't really say it's correct because they're looking at the wrong thing here, okay? So, with that being said,